I'm going to look at some more examples here in this video for integrating. And the first example we have here is t squared minus the sine of t. And this example we're looking at integrating our variable t, but also here we have a trig function. So to integrate this, it's very simple. We have t squared, so you increase the exponent, so that becomes t cubed over 3 minus, and then we have sine of t. And this is one of those integration formulas that we have to basically memorize for your trig functions, just like we did for the derivative. So we know that the integral of sine of t is a negative cosine t plus c. And be careful with the negative, so this would really be t cubed over 3 plus the cosine of t. All right, the next example, we have theta squared plus secant squared theta d theta. And notice here we're integrating with respect to theta. So if we integrate theta squared, that's our variable. So in this case, we could think of this as x squared plus secant squared x dx. But here our variable is theta. So we would have theta squared. So we increase that by 1. So we get theta cubed over 3. And secant squared. Well, if you look at your formulas here for the integral of secant squared, we're in luck because the integral of secant squared happens to be simply the tangent of theta. And then, of course, we must add our plus c. All right, here we have secant y, tangent y minus secant y dy. How can we integrate this particular trig integral? And if you stated first to rewrite this, again, we have a product, and we do not have a product rule for integration, so we're going to distribute the secant y. And if we distribute, we're going to get secant y tangent y minus secant times secant, we would have secant squared y dy. And now we have a form that we can integrate. And at first glance, you may say, wait a second, if we're going to integrate secant y tangent y, we have multiplication. Well, if we look at our formulas for integrating, we have a formula for secant y tangent y, and the integral happens to be secant y. And if you recall, when we were taking the derivative of secant, remember the derivative of our secant was secant tangent. So it certainly makes sense that the integral of secant tangent would be secant y. And then, of course, we have minus secant squared. And once again here, secant squared is simply tangent of y plus our constant. Okay, here we have the integral of cosine x divided by 1 minus cosine squared x dx. So if this is 1 minus, and this should be a 1 here, 1 minus cosine squared x dx. Again, we do not have a quotient rule, so how can we rewrite this integral? And this is going to require us to use some of your trig identities, and hopefully this one is somewhat obvious. 1 minus cosine squared. Remember, if you have 1 minus cosine squared x, that's going to be equal to sine squared x. And that's because sine squared plus cosine squared equals 1. So if we solve for sine squared, we end up with 1 minus cosine squared. So this becomes cosine x over sine squared x. And if we split this apart so that we have a sine squared on the bottom, so we can think of that as 1 over sine x, and then cosine x over sine x. So if we think about splitting this up, we have 1 over sine, which will become cosecant, and cosine over sine will become cotangent. And at this point, I think you're seeing why it's important to understand your trig identities. So those of you that had pre-calculus, and you realize now why these trig identities are important, because we can rewrite these problems into a form that we can integrate. And at this point, we have a formula for the integral cosecant cotangent, and it happens to be negative cosecant x. So never forget, when you're looking at your integration and you have trig functions involved, it's always a possibility that you can use your trig identities. All right, now here, the last several problems we're going to look at are how do we solve differential equations. And remember, we looked at this in the very first video in this unit, I believe, where we had a differential equation, which is simply an equation that involves your variables x and y and derivatives of y. So here we have the derivative of y dy dx equals 2x to the negative 3. So how can we solve this differential equation? Well, we want to solve for y. Now, to start off, we can rewrite this. Remember, in the previous unit we were talking about differentials, where we would take the dx and move it over. So we could think of this problem more like dy equals 2x to the negative 3 dx, and you could just kind of think of multiplying the dx to the other side. And from here, we want to integrate both sides of the problem, because if we're trying to solve for y, we need to get rid of dy. So we're going to take the integral of both sides of the equation. So we'd have the integral of dy, and then we would have the integral of 2x to the negative 3 dx. And when we integrate the dy, remember this is just understood to be 1 dy. So when we integrate, that would just simply become 1y, or simply y. And we integrate 2x to the negative 3, we would have 2x raised to the negative second power divided by negative 2 plus c. And we can simplify this by writing y equals, the 2's cancel. We can move the x squared to the bottom, so the 2's are going to cancel, and we would have a negative x to the negative 2 plus c. And we can move the x to the bottom, so we have a negative 1 over x raised to the positive second power plus c. Now this here is considered to be the general solution to this differential equation. So we solve this differential equation for y, and this is what we call a general solution because we do not know the value of c. Okay, later on we're going to see a couple examples here in just a few minutes how we can find more of a specific solution when we can solve for this constant. All right, so here we have another one. We want to solve this differential equation, dr d theta equals pi. And once again, maybe you can pause the video to see if you can solve this on your own. All right, so hopefully you took the time to try this one on your own. And if we look at this together now, we have dr d theta equals pi. And once again, we want to move the d theta to the other side. So we would have dr equals pi d theta. And once again, we want to solve for r. So that means we need to integrate dr equals the integral of pi d theta. And of course, if we integrate dr, again, that's understood to be 1 dr, so that's simply r equals the integral of pi d theta. Now keep in mind, everybody gets confused with pi. Pi is a constant, and our variable here is theta. So this would just become pi times theta plus c. And that is your answer. So again, we solve the differential equation here for r. All right, here we have another differential equation we want to solve. We have I'm sorry, this should say f prime of x equals 6x squared. But notice here we're given f of 0 equals negative 1. So here we can actually find a specific solution given that f of 0 equals negative 1. Well, to start out, we have f prime of x equals 6x squared. So just like before, we're going to take the integral of both sides. So the integral of f prime of x is going to be equal to the integral of 6x squared. And if we think of this, when we integrate f prime of x, well, certainly that's just going to be our function f of x. And the integral of 6x squared would become 6x cubed divided by 3 plus c. So we would have f of x equals 2x cubed plus c. And this here is the general solution. But if we use this given information here where f of 0 equals negative 1, and keep in mind when we say f of 0 equals negative 1, that simply means that when x is 0, our y value is negative 1. So if we plug that into our function here, then f of x, that's like saying f of x is negative 1, 2 times x cubed when x is 0, so that's 0 cubed plus c, and we simply solve for c. Well, 2 times 0 cubed cancels out, so we find that c is equal to a negative 1. So then we can plug that into our function, and we would end up with f of x equals 2x cubed plus c. Well, we know our c value is negative 1. So there, the solution to this differential equation is f of x equals 2x cubed minus 1. Now again, the only way that we can solve for this value, or this constant c, is if we're given some other information so that we can find the value. Alright, so here I have another example. So maybe, once again, you can pause the video to see if you can find the solve this differential equation. F prime of x equals 6x minus 8x cubed, given that f of 2 equals 3. All right, hopefully you were able to pause the video and you were successful in solving this problem. So let's look at this together. Once again, we're going to have to integrate both sides. So if we do that, of course, if we integrate f prime of x, that's just going to be f of x. And we want to take the integral of 6x minus 8x cubed. And if we do so, we would have 6x squared divided by 2 minus 8x to the 4th divided by 4 plus our constant. And simplifying this, 2 and a 6, we get 3x squared minus 2x to the 4th plus c. And once again here we have f of 2 equals 3, so that means when x is 2, our y value is 3. So if we substitute that down here, f of x is our y value, so that means 3 is equal to 3 times our x, which is 2 squared minus 2 times, in place of x we have 2 to the 4th, plus c. And if we solve now for c, we get 2 squared is 4 times 3 is 12 minus 2 to the 4th is 16 times 2 is 32. And then of course if we solve for c, 12 minus 32, and then we can add that over to 3 and we get 23. So then we can substitute that in for our c value, and we would end up with f of x equals 3x squared minus 2x to the 4th plus 23. Now, once again, you're not able to find this unless they give you additional information, f of 2 equals 3. Otherwise, you would have to stop with the general solution with adding on your constant.